Yesterday I actually didn't want to go because I was too hot. That exam.
When do you find out? Was it like, did they give you like a private
EGME 5 the model.
I got on the class
After all the grades. Just next to it. I got stumped. Sweat. I forgot it. It's like stressing us, but I figured it out. It's gonna.
Like after
I think it was just, I was like his own semester or something, but I think 5 days actually. You told me to lose one because.
Yeah.
Incredible. Thing. Went like traveling like.
at first day of the blackboard,
All right, it's 4 o'clock. Let's go and get started. Hi, good afternoon, everyone. How's everyone doing today?
Good.
Good. Somehow trying to stay cool, so I might have to take a break some point today. It's ironic, this is a class on fluid mechanics, but I think I'd rather be in a pool or something, enjoying fluids more directly than learning about its equations right now. But here we are. Okay, so plan for today. We're still just in the first week, so we're really just introducing the course. So today will be kind of a little bit more of an in-depth version of the slides that we covered on Tuesday. So Tuesday we went over just some very basic, introductory concepts in fluids. We defined what a fluid is. We went over a couple of its important properties like density and viscosity. So we'll be reviewing that again today, just because those concepts are really important. Before we actually start kind of the first, I would say, real topic, which is hydrostatics. We're going to start hydrostatics next week on Tuesday. Okay. Okay. So with that said, I don't think there's really any announcements. So your first problem set will be posted next week. So that'll be on hydrostatics. We haven't started hydrostatics, so I didn't want to post it just yet, but that'll be ready for you guys start of next week. The only assignment that we have right now is just the introductory assignment. So it's just you guys just need to send me an email. I think actually a lot of people have already sent me an email. I've responded to most of them, although I haven't been at my computer the last couple of hours, but you know, I'll get to them all before the end of the week. Okay, so make sure you send me an email before tomorrow, 11:59 p.m. and then that way you get full credit on the first assignment. Any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get rolling. Okay, so today will be a little bit of a more formal introduction to fluids, because you know, Tuesday we spent a lot of time talking about the syllabus and the course website as well. Right, today we'll go a little bit more in depth. Okay. All right, so the goal for the class today is really just to kind of establish our baseline, right? So, you know, from here on out, you know, starting next week, it's just going to be kind of go, go, go. And so, you know, a lot of these kind of basic concepts and kind of basic understandings of fluid properties, you know, we're going to assume that we kind of know them from. Okay. Okay. So let's kind of recall our definition of a fluid that we stated on Tuesday. So definition of fluid, okay, is a substance that will continuously deform under an applied shear stress. All right, and so if you apply a force to a fluid and you maintain that force, the fluid is going to continuously deform. Okay. Now let's dive into this a bit more. So I know we spent some time for this, right? So when I say continuously deform, right? So kind of the more colloquial or conversational way to say that is to say that fluids will flow, right? Right, and so a substance that's going to flow is going to continuously deform, right? So let's contrast that actually with the solid. So for a solid object, okay, if you apply a stress or if you apply a force to a solid object, it may deform, right? So you know you may experience some elastic deformation. But eventually, you know, because of just the way a solid is composed, because of the strength of the intermolecular bonds within the solid, it will eventually reach an equilibrium state. Right? So it may deform a little bit, but eventually it stops because it reaches that equilibrium state, right? Think of just a very simple case, right? So think of like, you know, just an object that's dangling, right? So if you take an object, you just dangle it in front of you, right? It may deform, right? So, you know, this pen here is very light. And so the deformations, any kind of elastic deformations this pen may have may be very minuscule, right? But, you know, this pen is being subjected to forces, right? So it's being subjected to gravity forces pulling it down, and it's being subjected to a force from my fingers that's keeping it up, right? So in other words, the solid object has reached equilibrium and that its motion eventually goes down to zero, okay? That's not true for fluids. But for fluids, if you apply a force, it's just going to keep flowing and flowing and flowing until basically something stops it, right? You can take a water bottle, you can turn it upside down, In that case, the water is subjected to the same forces as this pen, but that water is just going to spill everywhere because it's fluid, right? So that's kind of the main kind of distinction that we make between fluids and solid objects. It's just the ability for fluid to flow or continuously to form. Okay. Okay. So why is that? So the reason for this is you have to kind of go down to the molecular structure of a solid versus a fluid. Okay? Okay. So we're not going to talk too much about the molecular structure of a substance. This is kind of it. But I think it's useful to kind of look at this, when we're talking about a fluid versus a solid. Okay. All right. Because if you look at a fluid, right? So you can think of your very favorite fluid. The only one I can think of is H2O water because that's what I want right now because it's so hot, right? So for a fluid, right, we have all of these H2O molecules. Right? And I'm kind of drawing this pretty intentionally. Okay? Right. So each circle there represents basically a molecule of liquid. Okay. So for a liquid, right, even for a liquid, your molecules are going to be pretty closely packed together, right? So, I kind of tried my best, but, you know, basically for a fluid or a liquid, the molecules are closely packed, but they can slide past each other relatively easily. Right? So even though there may not be that much space, right? So for a liquid, the molecules are still packed relatively close together. The intermolecular bonds, or basically the amount of force that holds two consecutive molecules next to each other, are relatively weak, and so that kind of gives them the ability to slide. Thus, we get kind of the typical behavior of a fluid, which allows it to flow. Okay, you contrast that with a solid. Okay. So we look at the molecules that are inside a solid, and it's much more rigid. It's much more uniform. Okay? Right? And of course, and I know that not all solid molecular structures look like this. What I'm drawing here is probably closer to a metal, right? So a metal has a very uniform, very rigid molecular structure, right? But the kind of the defining characteristic of a solid is that each of these molecules are bonded very, very close together, right? So even though, these are separate molecules, they are very tightly bonded together, right? So it's very difficult to separate. You may be able to kind of, pull them apart slightly, but, for the most part, a solid will retain this structure. Okay? Okay? All right, so that's the kind of the primary difference, okay, between a fluid and a solid. And just since we're here, let me go ahead and draw you the molecular structure of a gas as well. So gases and liquids, for the most part in this class, we don't really make that much of a distinction. They kind of behave somewhat the same way, but on a molecular scale, they are quite different. So for a gas, right, a gas is the same way. So for a gas, the molecules can slide past each other very easily. It's just that there's a lot more empty space in between the molecules of a gas. Okay. And in fact, because of that, you could argue that gases will flow much more easily. And that's true, right? So gases tend to have much lower viscosities than liquids. And a part of that's just there's just a lot more dead space in a gas. Okay. So that's kind of the main difference, right? So that's kind of gives the fluids an ability to flow. Okay. Any questions on this? Okay. All right. So that's so this structure here and this behavior is true for all fluids, right? So even very viscous fluids, this is kind of what we understand. Right. And I think on Tuesday there was a question of, that we have some substances that, we don't necessarily characterize as fluids, but they have fluid-like behavior, right? So someone brought up the question of sand. So, you can kind of look at this analogy or look at this interpretation of a fluid and see why sand kind of exhibits that same property. Because sand particles kind of behave like this, right? So sand particles, again, they may be closely packed together, but the bonds in between individual sand particles are not particularly strong. So they just flow past each other very easily. Okay. The only difference is that with sand, right, a sand particle is actually much bigger than a molecule because we can actually see a sand particle, right? And so there's limits to how much sand or those loose packed types of materials behave like fluids. But in the bulk sense, you can consider them to be roughly the same. Okay. All right. So let's go ahead and change gears a little bit. Let's talk about dimensions and units. Okay. So kind of the slightly boring part of today, right? So this is the part that doesn't necessarily have to do with fluids, but it is an important concept for us to know. Okay. All right. So every physical property, every physical parameter, every physical variable that we use to describe fluids and kind of anything else in this world that we're trying to quantify has dimensions and they have units. Okay. Okay. So that concept itself is not new, right? So, you guys have been doing science for so many years now, right? So anytime you come up with some kind of, unit of measure, like length or velocity or acceleration, right? We know all of those have their particular units, right? So we're familiar with the SI unit system, the English unit system, all of those and so forth, okay? But let's make the distinction between dimensions and units, because there is a difference between them. Okay. So dimensions, you can think of them as the raw physical measures by which the variables are expressed. Okay. So dimensions you can think of them as almost like the types of units, but the units themselves are kind of the names for the dimensions, okay? So for example, right, dimensions are just the raw physical measures. So things like mass, things like length, things like time. Right? Right. So, we know that there's units of mass, right? So you can either go with kilograms or pound mass. There's units of length, right? We can go by inches, centimeters, and time, which only really has seconds. But But dimensions are just, what we consider just the raw measures by themselves, okay? The units, on the other hand, the units are simply just the names of the assigned dimensions. Okay. All right, so for example, right, the meter is a unit of length. Okay. And then the kilogram is a unit of mass. Okay. So I think a lot of people refer to dimensions and units interchangeably, but they are kind of slightly different, right? So think of units as just simply the names of the particular dimensions. Okay. Okay. So why am I bringing this up? So in fluid mechanics, in this class, we're going to be introduced to lots of, I would say, very new concepts and lots of new quantities that you've probably never viewed before in a previous class, right? So think of class on Tuesday, right? So we introduced the concept of viscosity. I don't think there's a concept in any other class that you've had where you've talked about viscosity, right? And viscosity is really just kind of the tip of the iceberg. So we have a lot of different quantities where, we're going to be learning them for the first time. And so when you're learning about a bunch of new quantities or variables for the first time, it's important to remember that, when you have a quantity in an equation or in an expression, they all have to be dimensionally consistent with each other. Okay. Okay. So in fluids, right? In fluids, we're mostly concerned with, units of just mass, or excuse me, dimensions of mass, length, and time. Okay. And in fact, what we can do is we can take a bunch of very common fluid mechanical quantities or parameters and express them in terms of their dimensions of mass, length, and time. Okay. So this system of dimensions, the mass, length, time, we'll often call the MLT dimension system. Okay. All right, so let's do a few examples. So if you look in the notes, right, so if you're following along in the lecture notes that I post, there's a huge table here. We're not going to go through every single one of these. That's crazy. But also just a lot of these are not, they're just not relevant right now. But let's go over a few of them just so that you kind of get an idea of this, or kind of get used to this mass, length, time, dimension system. Okay. Okay. So let's start very simple. So let's start with velocity. Okay. I think when you're getting used to the mass, length, time, dimension system, it actually kind of helps to work backwards. Because, I think if you ask someone before coming to this class, what are the units for velocity? I think most people would say something like, meters per second or kilometers per hour or miles per hour, things like that. Okay. Now take that unit system and think, what are the dimensions that these units are representing? Okay. Okay. Actually, let me do this. Let's make a table. Okay, so first column will be the quantity. Next column will be its MLT representation. Okay. So for velocity, you know, we know the units for velocity are meters per second. If we express that in terms of our MLT dimensions, that is a length divided by time. Okay. And so whenever you have a quantity in the denominator for dimensions, usually we raise it to the -1 power. Okay. So velocity would be length times time raised to the -1 power because time is in the denominator. Okay. Okay, and then let's make another column here as well for an SI unit example. Okay. Okay, so we know for velocity, we know the units for velocity are meters per second. Okay. Right. So for the SI units, you know, I'll use a division sign there just because that's how it's traditionally expressed. But for our dimensions, let's use the -1 exponent. Okay. All right, another common one that we're going to see is acceleration. Okay. So acceleration, we know the SI unit for that is meters per second squared. And so its dimensions for that is going to be L times T raised to the -2 power. Okay. Okay. So let's do a little more of an interesting one. So one that doesn't quite have a convenient expression here, but let's look at force. Okay. All right, so force is interesting because, you know, we know that SI unit for force is newtons, right? But there's no dimension for force, right? So we're looking at mass, length, and time, right? So how do we express force in terms of its dimensions? So we know the SI unit. The SI unit for force is newtons, okay? And also what we know from Newton's law is that force is equal to mass times acceleration, right? F is equal to ma, okay? Let's use that equation there to express the dimensions of force, right? So we know force is the product of a mass times an acceleration, right? We know acceleration, we just did it. And then we just need to multiply that by mass, which is one of the building blocks of our dimension system. So the dimensions for mass, or for force, excuse me, is mass times length times time raised to the -2 power. Okay. All right, let's do one more. I literally have a table of like 20 of these in the notes. So, you know, we can do this for an entire lecture, but you know, it's already getting old. I can tell. Okay. All right. So another common one that we'll see, you know, especially next week. So next week, this is going to be a big theme for the next couple of weeks, is the concept of pressure. All right. So pressure is defined as a force divided by an area. Right? A pressure is essentially a force distributed over an area. Okay. The SI unit for pressure doesn't necessarily correspond to the dimensions, but the SI unit for pressure is a Pascal. Okay. Named after a guy, scientist who made a lot of contributions to the area of hydrostatics. Okay. Okay. But that doesn't necessarily mean that our dimensions will be quite simple for this. Okay. But luckily, we just solved for the dimensions of force. We just have to divide that by the dimensions of area, okay? Okay. And area itself is very straightforward. We know area is just length squared, right? Okay. So let's take our dimensions for force and then divide it by length squared. And so if we do that, we get mass, okay? We have a length in the numerator for force. That's going to cancel out with one of the lengths in the denominator, and then there's going to be one left over. So it's going to be mass times length raised to the -1 times time raised to the -2. Okay. Question, yes.
Yeah, why not just, I see there's one for stress and pressure, why not just keep it under the same pressure slash stress? Why do they use different?
Yeah. No, that's a great question. So pressure and stress have the same units, they have the same dimension, but what they represent in a fluid is actually slightly different. So we'll go over that. We'll go over that a little bit next week, but just to kind of give you a little preview. So if you have a fluid element like this, when you talk about pressure, pressure is always a normal force. So it's a force that gets applied normal to whatever surface that you're looking at. So pressure gets applied like this. So it's a force that's distributed over that area, but it applies it kind of directly to the object. A stress, on the other hand, most of the time when we talk about stress, we think of shear stress. And so stress also is a force on that area, but it's going to be applied parallel to that surface instead of perpendicular. Yeah. So in green right there, that's the stress. Yeah. So that is a big point of confusion. So I'm glad you asked. But yes, even though stress and pressure, same units, same dimensions, but the way that we interpret them and what effects they are. Yeah. Question, yes.
So looking at the table, strain is unitless.
Yes.
Does that mean it's like a percent, like something is some percent of something else?
Yep. Yep. A lot of times when you have dimensionless numbers or dimensionless quantities in science, a lot of times they represent some kind of percentage. Sometimes they can also represent ratios as well. And so later on in the class, I think probably around week 10, we'll cover the idea of a dimensionless number. So things like a Reynolds number, Prandtl number, things like that. So those dimensionless numbers are ratios. But for strain specifically, that's interpreted as a percentage. Yes. All right. Any other questions on this? Okay, good. All right. So the reason I bring up dimensions and units is that we're gonna be introduced to lots of different new concepts and lots of different quantities, right? And a lot of times you're going to be looking at these new quantities in an equation, right? So one thing that's important whenever you have an equation is that every term in an equation has to be dimensionally homogeneous. Okay. Which is kind of a fancy way just to say that everything in the equation has to have the same dimensions. Okay. But I guess the real word for this is dimensional homogeneity. And I always never sure if I spelled this correctly. I think it's supposed to. Okay. All right, so this is always good to check. And in fact, if you think about the equations in terms of dimensional homogeneity, you may kind of glean some important understandings or interpretations of that equation. Okay, so let's do a simple example first. Okay, so this example is coming straight from just classical mechanics, which is that the velocity of an object, final velocity, is equal to the initial velocity of the object plus the acceleration times time. Okay, so that's just a very simple. I think this comes from projectile motion, although it's true for any object, right? And so if we have an equation like this, what we're saying is that every single term in this expression, right? So everything that's separated by an equal sign or a plus or a minus has to have the same dimensions, okay? And so if we look at term number 1, term number 2, term number 3, all of these should have the same dimensions. Because what we're saying is that, we're adding these together, we're setting them equal. In order to do that, they have to have the same units, the same dimensions, okay? Okay, so for the first two, it's pretty straightforward. Both of these are velocities, right? So we know velocity has dimensions of length times time minus 1, length times time minus 1, right? So that checks out, right? And so both of those have dimensions of velocity. If we look at this last term here, acceleration we know has units or dimensions of length times time to the minus 2. And then time has dimensions of, well, time. Okay. Okay. And so if we multiply these together, we can see that we have 1 time in the numerator, 2 times in the denominator. One of them is going to cancel out. What we end up with is length times time to the minus 1. Okay. Okay. So all that is good. Okay. So that is so everything in this expression is dimensionally homogeneous. All right, so let's do another example. This one's going to be a bit more complicated. Okay. So this is an equation actually from our very last unit. So, kind of a preview of 16 weeks into the future, or 15 weeks, right? So let's look at the settling of a spherical particle in a stagnant fluid. So this is a question of drag forces, basically. Okay. So what this equation is basically telling you is that if you drop a spherical object in a fluid, right, and you can drop it in air is technically a fluid, air is all around us, eventually it's going to reach a terminal velocity. And so its velocity is going to stagnate, okay? That's because basically there's going to be a balance of forces between the weight of the object and the drag forces, or air resistance or fluid resistance against that particle, okay? Okay. And so this equation, we have mass times gravity minus pi over 8 times the drag coefficient times the density times the velocity squared times the diameter squared is equal to mass times the derivative of the velocity. Okay. So a little bit more complicated than the previous one. Okay. So we're not going to go through the derivation of this equation. We'll do this in week 15. But the only reason I bring this up now is that, even for a complicated equation like this, we can go through the motions or go through and check whether every term here is dimensionally consistent, homogeneous with each other. Okay. Okay. So let's start with the first term, mass times gravity. Okay. So mass has dimensions of mass. Gravity is the acceleration due to gravity. So that's a mass times an acceleration. So you have mass times length, t minus 2. Okay. All right, so there's no simplifying there, so nothing cancels out. So we just kind of leave that as it is. Okay. I'll leave the second term alone for now, just because that's the most complicated one. But let's go to the third term. Okay. So ideally, that third term should have the same dimensions as mass times gravity, right? So we should get mass times length t minus 2. Okay. Okay, so this last term here, we have a mass, right? So the dimensions of mass is just mass. Okay. Right. And then we have dv dt. So dv dt there is the derivative of the velocity with respect to time. Okay. Now, this is the first time we've seen a derivative in this, right? So when we have a derivative, we have to take into account the dimensions of the derivative as well. Okay. So let's look at the numerator for the derivative first. Okay. So the numerator for the derivative, we have velocity. So we know the dimensions of velocity. Right? So dimensions of velocity is length times time minus 1. Okay. And then we're taking derivative of the velocity with respect to time. And so in the denominator, we're going to have time. Okay, so that time in the denominator represents the dimensions of dt. Okay. All right, and so if we work this through, we can see that we have basically 2 times in the denominator now. So we have t to the -1 divided by t, so that gives us t to the -2. And so this gives us mass times length times time raised to the -2 power. Okay. Which is consistent with mass times gravity. And so we're all good for now. Okay. All right, and so finally, let's tackle the big boss in the middle here. Although in the grand scheme of things, this term itself is not too complicated, because actually a lot of this is non-dimensional as well. Okay. All right, so we have the product of essentially 5 different numbers here. So we have pi over 8 times the drag coefficient times density times velocity squared times diameter squared. Okay. Okay. So when you have a complicated expression like this, all you really have to do is just break it down kind of one thing at a time. Okay. All right, so let's look at pi over 8 first. Okay. Okay. So pi over 8 is just a number, right? And so numbers by definition do not have any dimensions at all. Right? I know pi is an irrational number, but an irrational number is still just a number. Okay. All right, next we have the drag coefficient. So drag coefficient is another example of a non-dimensional number. Essentially what it represents is it just represents the ratio of just the amount of force that's upstream of an object and downstream of an object, right? Because whenever you have an object that's being subjected to a flow field, it's going to be subjected to some drag force. And so that drag coefficient is just the ratio, okay? So the drag coefficient, just like any other thing that is characterized as a coefficient, also has no dimensions. So you see, once we get to kind of external flows at the end, there's drag coefficients and there's lift coefficients, okay? So, we'll get into that a lot later on. Okay, next we have rho. So rho here represents density, right? So we talked about density on Tuesday. So density is a mass divided by volume, right? So the dimensions for this is mass, and then we have the dimensions of volume, which is length cubed. Okay. Although I guess if you want to be consistent, it would be mass times length to the -3 power. Okay. But I'm running out of room, so do mass over length cubed. Okay. Okay. Next, we have velocity squared. So we know the units for velocity is length over time. Okay. But we're squaring this, and so we need to apply the square to each of those dimensions there. So we have length squared divided by time squared for them. Okay. All right. And then finally, we have diameter squared. Diameter has dimensions of length because it just measures kind of the diameter of a circle, or in this case, a sphere. And so the dimensions for that will be length squared. Okay. Okay, so let's go ahead and multiply all these things together. And if all goes well, we should get units of force, essentially. So mass times length divided by time squared. Okay. Okay. So if we multiply all these together, we have mass divided by length cubed, multiplied by length squared, divided by time squared, times length squared. Okay. Right. And so the length cubed on the bottom is going to cancel out completely because we have a length to the power 4 on top. So that most of the length is going to cancel out, right? The mass and time have nothing to cancel out for them. And so you have mass times length times time minus 2. Right? Okay. And so what we see is that middle term also is dimensionally consistent or homogeneous with the other two terms in that expression, right? So everything here has units of force. All right, any questions on this? Okay. All right, so dimensionality or dimensions for units, really important concept. And so it's one thing we're going to come back to quite a bit. Okay. And in fact, in the middle of the semester, we're going to go over something called dimensional analysis, or Buckingham Pi theorem, where this kind of comes back in spades. Okay. All right, but the last thing I wanted to go over today, which is going to take us all the way to the end of the class, is we're going to talk about different fluid properties a bit more. All right. So the fluid properties are the different types of, characteristics or physical quantities that describe how the fluid is going to behave. Okay. Okay. So there's a lot of different fluid properties out there. I will say that, in this class, we're not going to deal with a lot of them actually. Even though a lot of them are really fascinating, really cool. It's just that fluids is such a huge, deep subject. For an introductory class like this, there's only so much we can go over. But I at least wanted to mention a lot of them today, just to kind of mostly just acknowledge them, just to know, just to tell you that I know that they exist. I know that surface tension is a thing. But for a lot of these things, we're not going to cover them too much in this class. Okay. All right, so we already covered some of this on Tuesday, right? And so the first one that we talked about on Tuesday was the density, right? Density is a very important property for fluids. It essentially tells you how dense they are, how much mass is in the fluid. Okay. So I'm not going to spend too much time talking about it. Right, so we know density is the ratio of the mass of the substance relative to how much volume it occupies. Okay. All right, and so density, like we mentioned on Tuesday, has the symbol rho. Okay. I apologize. I don't know if it's because it's hot, but my pencil is kind of behaving weird. Right. So rho here is just the mass of the substance. Divided by volume. Okay. And we already went over its dimensions. Its dimensions is mass divided by length. Okay. Okay. So I think we also mentioned on Tuesday that density of a fluid is sensitive to temperature and pressure. Okay. Right. So typically, if you raise the temperature of a fluid, you're also going to lower its density and vice versa. Okay. If you're curious about why that happens, I know I said we wouldn't refer to it again, but it has to do with how the molecular structure of the fluid is behaving and how it responds to different temperatures. Okay. So at higher temp, so I'm not going to write this down because it's not something I'm going to test you guys on really. But typically, as you heat up a fluid, you add more energy to the system, right? Temperature is really nothing more than just a measure of just how much internal energy is within the system. Okay, so if you add energy, you add heat to a fluid, what that does is that energy is absorbed essentially by the molecules in the substance. And so if you give them more energy, they're able to kind of move around and jostle a lot more. And that creates more space in between the molecules. Okay, and the more space there is between the molecules, the less dense it's going to be. Okay. Pressure has the opposite effect. So pressure kind of represents how much force is being exerted onto the fluid, right? As you increase pressure, you essentially are kind of squeezing the fluid particles or fluid molecules together, okay? So density tends to go up with pressure. So temperature and pressure kind of have opposite effects on the density. Okay. One other way that we often report density is we often use the idea of the specific weight. Okay. So specific weight is just density multiplied by gravity. Right? Which is still a ratio, but instead of being the mass of the substance divided by volume, we instead have the weight of the substance divided by volume. All right. But besides that, there's really not much more to talk about with density. Okay. Any questions on density? Okay. All right. So the other fluid property that we talked about on Tuesday was the viscosity. All right. So viscosity, remember, it represents the fluid's resistance to flowing. Right? And so fluids with high viscosity or highly viscous fluids will tend to feel stickier, right? Because fluids that are stickier just will not just flow as easily. Okay. All right. So that's kind of the informal definition of viscosity. If you want to get a bit more technical, viscosity actually describes the relationship between shear stress and strain rate in a fluid. Okay. And so what are these quantities here? So if we have a parcel of fluid, so we have just a rectangular fluid particle here, okay? All right, and let's say that we apply a shear stress, right? So remember earlier I mentioned shear stress is essentially a pressure, but we apply it parallel to our surfaces here. Okay? Where this tau here is a shear stress. Okay. Right. So what do we know about fluids, right? So we're applying a shear stress to a fluid. We know it's going to continuously deform, right? And so applying the stress will cause the top and bottom layers to move at a velocity. Okay. All right. And so the top layer, because we are applying the shear stress to the right, it's going to start moving to the right. Okay. Right. And the bottom layer, it's going to start moving to the left. Okay. Right. And so we have kind of a parallelogram kind of situation here. All right, and so applying that shear stress is going to cause a difference in velocity from the top and the bottom, right? So the top is going to be moving at a velocity, bottom is going to be moving at a different velocity, right? And that's going to occur over a set distance, delta y, okay? And so the viscosity, and you know, I'm not going to get too much into this just because this is a bit more advanced, but just in case you're curious, right? So viscosity sets this relationship. So the relationship between the shear stress that we're applying is equal to the viscosity of the fluid multiplied by the strain rate. Okay. So on the left here, this tau, this is our shear stress. This right here, this du dy, this is our strain rate. Okay. All right, and then the quantity that connects the two, that, you know, on the one hand, you can say makes this dimensionally consistent is the viscosity. Okay. So in some sense, you know, you can look at this and say, you know, that's actually a pretty simple equation, right? So for a quantity that actually has quite a bit of complexity, viscosity actually goes pretty deep. You know, this relationship here is actually quite simple, right? It's essentially just a proportionality equation, right? You take the strain rate, you multiply by viscosity, that gives you the shear stress. Okay. Okay. So the way to interpret this formula and the way to kind of connect it to our, you know, our understanding of viscosity, being that, you know, viscosity represents our resistance to flowing, right? If we reimagine the shear stress, right? Because how do we apply shear stress to a fluid? Well, you have to apply a force to it, right? So the shear stress often represents some kind of external force. Right? So some kind of external force that you're going to apply to the fluid with the intent of making it flow, right? And the strain rate here, right, which is essentially a difference in velocity over a certain distance, that's essentially our flow, okay? Right, I would say those are kind of the more informal ways that to think of these quantities here. Okay, question, yes.
Is the U the velocity?
Yes, U is velocity, yeah. Yeah, I'm sorry. So yeah, so sometimes I use U, sometimes I use V for velocity. Yeah, thank you for that. All right, and so if you think of shear stress as an external force, strain rate as flow, viscosity represents how much force or how much external force that you need to get a certain amount of flow, right? And so if your viscosity is higher, right? So let's say you have viscosity of, you know, honey, right? You need a lot of force, a lot of shear stress in order to achieve flow, okay? So that's kind of where that idea of viscosity comes from, where viscosity is, you know, resistance to flowing. That comes directly from this equation right here. Okay? Viscosity is just this relationship between shear stress and strain rate. Okay. Okay. Any questions on viscosity here? The interesting thing about viscosity is that, you know, sometimes when people talk about viscosity, they think of it as kind of like the thickness of a fluid. I don't really like that kind of description because, you know, it's not really thickness, but, you know, intuitively we think of thick fluids as viscous fluids, right? And there's a very famous saying that was popularized by a certain movie that blood is thicker than water. Right. And so I can tell you with certainty that when this line was muttered, they were not thinking about fluid mechanics in the least. Okay. But it's also fun to think about, you know, is blood actually thicker than water, right? And so let's look at the viscosities of water, air, and blood at room temperature. Okay. As viscosity, just like density, does change with temperature. I think that was brought up on Tuesday too, when we're talking about motor oil, right? And so, you know, we have, when you're comparing viscosities, you have to make sure that they're at the same temperature. Okay. Okay. So let's look at water first. Okay. It's also good just to kind of put numbers to these, just so that you start to kind of build just a physical intuition of these of certain quantities. Okay. The viscosity of water is 8.9 times 10 to the minus 4 Pascal seconds, okay? Or poise, right? So that's kind of the SI unit for viscosity, okay? And let's look at the viscosity of air, right? Remember, what we interpret as viscosity, we expect air to be much less viscous than water because air flows extremely easily, okay? Mostly just because air is a gas, right? So the viscosity of air is 1.81 times 10 to the minus 5 Pascal seconds. Okay. Right, so we can see that that's true, right? And so air is a complete order of almost 2 orders of magnitude lower viscosity than water. Okay. But then what about blood? Okay, so the viscosity of blood is 2.87 times 10 to the minus 3 Pascal seconds. Okay. Right, and so because that last number there is 10 to the minus 3, it's actually true. So blood actually is bigger than water, right, as measured at room temperature. Okay. I remember the first time I showed this to my wife. I said, honey, blood is actually not thicker than water. Actually, it's more viscous than water. And somehow I survived, and somehow she married me. So I guess all is well that ends well. Okay. All right, so density, viscosity, those are definitely the most important properties. Let's just go rapid fire through a few more, just to kind of acknowledge that they exist. But again, we're not going to do too much with these other properties here. Okay. Okay, so next one is compressibility. So if you are interested in going into the aerospace field, this is definitely a property that you will get to know. Okay. So compressibility describes how well a fluid's volume and density change as a function of pressure. All right. So like I mentioned, when we went over density, right? As the pressure increases, pressure basically tells you how much force is being exerted on the fluid particles, right? As pressure increases, it kind of squeezes the fluid particles kind of closer together. And so what you expect is that as you increase the pressure, the volume will decrease and the density will increase, okay? But the relationship or how well a fluid actually, makes that change depends on the fluid itself, right? On the one hand, you have some fluids, mostly liquids. Okay. Right. So with liquids, like we said, the molecules for liquids are already very tightly packed together, right? There's not that much room in between the particles. They can slide past each other pretty easily, but there's really not much more room for them to squeeze, okay? So liquids are often what we call incompressible. Okay? Because for liquids, no matter how much you increase the pressure or even decrease the pressure, the volume is not going to change. The density is not going to change, right? So the density and volume of a liquid, pretty independent of pressure, right? You can squeeze and squeeze all you want. A liquid is not really going to change its volume, okay? So compressibility is definitely much more of a property of gases. Okay. Right, so gases can be compressed just because there's just a lot more empty space in a gas, okay? But surprisingly, and surprising in the sense that just the way that I presented to you, actually a lot of gases behave pretty incompressibly as well, okay? And so if you're just looking at standard conditions, right? So basically like, room temperature, sea level, things like that, right? Most gases actually behave pretty incompressibly, right? So, you can't take a bundle of, of air, I know it's really hot in here, but you can't take a bundle of air and just kind of squeeze it as much as you can, right? That gas is still going to be pretty compressible or incompressible, excuse me. Okay? So compressibility, for the most part, really only becomes a factor at extremely high pressures and also at extremely high speeds as well. Okay. So if you're designing an aircraft engine, compressibility is certainly something that you'll take into account, just because the air or the velocity of air that's going through an aircraft engine is much, much higher. And so compressibility becomes much more of a factor at that point. Okay. But for most standard conditions, and for this class, that's where we're going to operate. We're going to be looking at mostly standard conditions in this class, room temperature, fairly modest speeds. Most of the time, we're going to consider our fluids to be incompressible. Okay. Mostly just because it makes the analysis just so much easier. Okay. Because if you have to account for the fact that a fluid's density can change with pressure, that actually complicates things a lot. Okay. So if you're interested in learning more about compressibility, we do have a class in aerodynamics 433. We do offer that in the spring. And so in that class, you'll definitely get into the, you'll definitely talk more about compressibility and how that changes your analysis. Okay, any questions on compressibility? Okay, all right, next one on kind of the carousel of different fluid properties is vapor pressure. Okay, so vapor pressure might have been something that you learned in your chemistry course, but basically, if the idea of vapor pressure is that when you have a liquid that has a free surface, so basically there's an interface between a liquid and air. Okay. Okay. And so at the interface of just any liquid and any gas, right? What tends to happen is that some of the liquid molecules will just kind of automatically kind of be ejected into the gas. Okay. All right. So in other words, if you have a glass of water, okay. So here we have a liquid. Our liquid is the water. It's connected to a gas, which is air. Okay. So just naturally, what happens, just as a result of just the latent heat of just the environment, right? Some liquid molecules will just naturally just kind of eject themselves from the liquid interface. Okay. Now you might look at this and say, is that evaporation? A little bit. And so evaporation does contribute to the vapor pressure, but vapor pressure kind of more measures how much of these molecules are leaving as a result of this process. Right. So the gaseous vapor. Okay, so there's basically a layer of vapor that's right near the liquid surface, right? And so that gaseous vapor creates a pressure, which we call the vapor pressure. Okay. And I'm sorry, I didn't complete the drawing here, but it's not just one molecule, there's multiple. Okay. And the molecules can come back, right? And so once it enters the vapor, it can come back to the liquid. Okay. So you also have particles that come back here. Okay. But basically there's kind of a thin layer above the liquid, where you have kind of liquid molecules that are kind of, kind of almost kind of like bouncing up and down. So you can kind of think of it. Okay. Okay. All right. So the vapor pressure is very highly dependent on temperature. Okay. In fact, as you heat up the liquid, right? As you heat up the liquid, more and more of these molecules are going to escape. All right. So heating up the liquid actually increases the vapor pressure. Okay. Right. And the reason for that being is that, remember, temperature essentially adds energy into the system. And so the more energy you give the molecules, the more tendency they have to kind of just escape and just kind of, get out of there. Okay. And in fact, you can actually increase the vapor pressure up to a point where it matches the atmospheric pressure around the liquid. Okay? So when the liquid is heated enough, such that the vapor pressure equals the atmospheric pressure, okay? Right? And so when this happens, the vapor pressure, there's really nothing kind of pushing the vapor back, okay? Because what happens right here, right, kind of in a typical scenario, right, the vapor pressure kind of ejects the fluid, but then the atmospheric pressure essentially pushes the particles back. And so the particles, don't get too far from the liquid. And so if you leave a bowl of water out in a room, it's mostly still going to be there, because even though there's going to be water molecules escaping, the atmospheric pressure essentially pushes it back, okay? But if you heat up the liquid enough such that the vapor pressure can kind of exceed or even, or equal the atmospheric pressure, there's not enough force from the atmosphere enough to push the molecules back, okay? So you kind of have this rapid evaporation of fluid or liquid that comes off the water, okay? And so this point here has a name that, is a bit more, informal. So we call this boiling. Okay. So boiling is what happens when you heat up a liquid enough such that, you have a rapid, exit of a bunch of these liquid molecules from the vapor. Okay. And so if you've ever been to the mountains, right, you go to higher and higher elevations, that water boils a lot more easily, right? And the reason for that is not just because it's colder in the mountains. The reason for that is that higher up in the mountains, the atmospheric pressure is much less, okay? Because as you get further and further away from sea level, atmospheric pressure drops, okay? And so it takes a lot less energy, a lot less heat to actually bring water up to boiling temperatures. Okay. Any questions on that? Yes.
And is this also the reason for that classic demonstration where you put a cup of room temperature water in a vacuum chamber and it boils?
Yes. Yeah, exactly. So in that case, it's the same idea as, boiling water in the mountains, but in a vacuum chamber, you kind of forcibly remove the atmospheric pressure. And so there's nothing really kind of holding the water back at that point. So just the natural energy from the water just kind of pushes it out, and there's nothing to push it back in. And so that's how that demonstration works. Yeah. Great observation. Okay. All right. One last property before we head out for the week is surface tension. Okay. Okay. So surface tension, I think, is one of the more cool aspects of fluids that we unfortunately will not do anything with in this class. But if you know about surface tension, right? If you have, again, kind of an interface of a liquid and a gas, there's almost like a very thin, almost like skin that forms on top of the liquid, which can support a very small amount of weight. Okay. Right. It's not much, but if you ever looked at like a water striding, bug, right? So those bugs seem to kind of float right on top of the water, right? So what's happening there is that the bugs are so light, they have so little weight that they can kind of skate on the surface of the water just based on the surface tension. Right. Right. It's also the reason why, if you have a droplet of water, right? So you have water that's kind of falling from the sky, water droplets form into spheres. Right? And the reason for that is because of surface tension. Right? So why does this happen? Right? Normally, right? Remember what we've kind of been talking about today, that a liquid or a fluid, or in this case, is a liquid is composed of a bunch of different particles together. Right? Ideally, a water particle or liquid particle likes to be surrounded on all sides by other liquid particles. Okay. Right, so you have a typical fluid particle here, right? We've already said that the intermolecular bonds or the interparticle bonds are weak, but they're still there, right? And so if you have particles on all sides, okay, right? This is good because, right, what happens is that, there's relatively weak bonds that form in between the particle and all of its neighbors, right? And so we have this kind of relatively weak bonds, but, that they're there. And what the particle likes to do is it likes to kind of spread this kind of bond energy to all the particles that are around, right? So a particle like this, it's a happy little dude, right? So he has friends on all sides. Okay. What happens at the surface, right? At the surface, there's a section or a part of the fluid particle where it's not surrounded by other liquid particles, right? Okay. So on the surface, you may have a particle like this, but it may only be surrounded on, a few parts of it, right? And so those bonds are going to form, right? But normally it's used to having, other particles around here, right? But since those aren't there because this particle is on the surface, what ends up happening is that the bonds that it forms with its immediate neighbors, right? It basically takes the energy that it would use to form the bonds on those sides and instead increases those bonds onto the ones next to it. Okay. And so because of these increased bonds here, that kind of forms our surface tension. Okay. All right, so that's the 5-minute explanation of surface tension. But surface tension in reality is a lot more fascinating. There's a lot more kind of to it, especially with the geometry. But I think that's enough for this. Okay. Any questions on this before we wrap it up for the week? Okay, all right, so that's all the time we have for this week. When we come back on Tuesday, we'll be starting hydrostatics, which is kind of our first real unit. Okay, so thank you guys for coming today. I hope you guys have a good weekend. Hope you guys stay cool, and I will see you guys next week.
Yeah.
Yeah. When you do the.
Yeah.
You.
Yes.
You plus me.
Yeah, that was a little of a mistake. They could be you, but going in opposite direction. So I was going off another one, off another definition, but it's you and you, just going in opposite direction.
Okay, not the plus.
Not the plus. I would, the DU comes from, if you have the bottom surface is stationary, then the top's going with the certain DU, so it's the difference between the velocity. But the way I drew it, both are going with a certain velocity. So it's just you can think of the DU as like a difference between the difference. Yeah.
It's one that has.
Yeah.
Same.
Yeah.
Yep, yes, yeah. Yeah, so you can, so the Zoom link is on the website, so feel free to join. The only days that you have to be here are. Every other day. you can join.
I only plan on staying home on Tuesdays, it's just this flag, I don't want to do an hour.
Oh, for sure, for sure.
That's cool.
Yeah. If I could do that, I would do that. Contractually obligated.
Thank you.
Yeah. Hey, what's up?
I just ask, like, so you guys post the notes on the campus?
I don't post my written, I post these notes, the ones that I.
Oh, yeah.
Because these ones are a bit
Yeah,
more
not the
organized.
same thing.
These ones are kind of a bit messy in
Yeah.
terms of,
Yeah,
They'll
because
be
I
like-
get they post every 10 minutes.
Oh, I see. I post all the recordings on Canvas as well. So you can look at the
Well, I
recordings
my
and look at the notes.
class.
Yeah, because I guess I'm having dropped
Oh,
it
you're good.
from my
Yeah.
work.
That's him.
Oh, I see. Yeah, no problem. And so same thing I told him too. So I mean, I stream all the lectures too. So if you want to watch them, that's fine.
Thank you.
Yeah.
Have a good night.
You too. Never mind.